Next up, we're going to look at inverses of linear transformations. Now remember, a linear transformation is a function. So anything you learned about inverses of functions will apply here as well. If you've got a function f, if it has an inverse, then we call that inverse f, well, we denote it with f raised to the negative 1. And those two functions undo each other. Or more formally, if you plug the inverse into f, or if you plug f into its inverse, all you get out of it is just x. So what we're going to look at here is inverses for linear transformations. So first up, let T map Rn to Rn be a linear transformation defined by a times x. Now notice this is Rn and so is this. In order to have an inverse, if you're going from, if you're dealing with Rn, these have to be the same size. They have to have the same dimension. T is invertible if and only if the matrix that goes with it is invertible. And if T is invertible, then its standard matrix is A inverse. So let's look at a few examples. With these, it says describe the inverse of the following transformations of the plane. So on this, we're really just going to talk about it in terms of what it does to the plane. If you have a rotation of 10 degrees counterclockwise, the inverse of that would be a rotation of 10 degrees clockwise. Or, this is the same thing, but it's just another way of mentioning it or describing it. You could also call it a rotation of 350 degrees counterclockwise, because both ways will turn the plane back to where it originally was. All right, reflection across the line y equals 3x. Well, reflections are interesting because if you reflect the plane over a line, to get it back to the original state, you just flip it back over that line again. So reflection across the line y equals 3x, the inverse of that would be reflect across y equals 3x. So that's kind of interesting. Reflections are all their own inverses. And let's see, a horizontal contraction with k equals 0.3. The inverse of that would be a horizontal expansion with k equals, well, it'd be the reciprocal of that, 1 over 0.3. That's kind of an ugly way of writing that, so let's rewrite it. 0.3 is 3/10, so the reciprocal of that would be 10 over 3. All right. Let's look at this next example here. It says the inverse of this, find the inverse of this linear transformation if it exists, and write it in the same form. Okay, so this is kind of like what we did at the beginning. This maps R3 to, let's see, how many of these do we have? 1, 2, 3. That's a typo right there. That's supposed to be x plus y plus z. So it maps R3 to R3. And the matrix for T that's a typo there too. That's supposed to be 4z minus x. So the matrix we'd get here for this top line would be 0, 3, 2. Notice all we're doing there is we're taking the coefficients of x, y, and z from here. So for this one, it's going to be 1, 1, 1. And then for this one, it's going to be, let's see, -1, 0, 4. All right, so if that's my transition matrix, actually, I want to call that A instead of T. So we're supposed to find the inverse of the linear transformation. Well, from there, we need to find A inverse. And we know how to do that, but I'm going to use the computer to do it. A is, let's see, 0, 3, 2, 1, 1, 1, negative 1, 0, 4. I'm taking the determinant there just for fun. A determinant of negative 13 means that the inverse is not going to be pretty. Let's see, inverse of A. Yeah, it's all these numbers, and they have a denominator of 13, so they're not very nice decimals. So let's do that again. We get this. Now, I'm going to write this out slightly differently. A inverse is going to be, I'm going to factor that 1/13 out. And I'm going to write the rest of these as just negative 4, 12, negative 1. And 5, negative 2, negative 2. And negative 1, 3, 3. All right, so that's the inverse matrix of the linear transformation. So T inverse of x vector is A inverse x. So that's not quite our answer because, I mean, it is the answer, but it's not written in the form that was asked. It says write it in the same form. So we want to write it out like this. So T inverse of x, y, z equals, see, really all we have to do is come over here and multiply this by x, y, z, and that'll give it to us. So it's going to be minus 4x plus 12y minus z, 5x minus 2y minus 2z, then minus x plus 3y plus 3z. So this is the inverse linear transformation of the one that was given up there.